All right, welcome back, everyone. Right now we have Nick Ball, data science at Dot Science, presenting on chaos and pain management. Chaos and pain in machine learning. Well, same thing. And the DevOps for ML Manifesto. By way of background, Nick has been a data scientist since the early 2000s. After obtaining an undergraduate degree in geology at Cambridge University in England, he completed master's and PhD degrees in astronomy at the University of Sussex. Did I say that right? Yeah. Nice. Then moved to North America, completing postdoctoral positions in astronomy at the University of Illinois and the Hertzberg Institute of Astrophysics in Victoria, BC, Canada. Machine learning has been part of his work since 2000, first applying it to large astronomical data sets, followed by wide ranges of applications as a general data scientist at Skytree, Infosys, Oracle, and now Dot Science. Please welcome Nick Ball.
Thanks very much for the introduction, and thank you very much for everybody coming here today, and to the organizers of the conference for giving me the opportunity to speak. My wife's a nurse, so she knows about pain management, but I can talk about managing chaos and pain in machine learning. This is the outline of what I'm going to talk about in the next 20 minutes. So it comes in three parts. Firstly, efforts in our AI today, followed by what is needed to improve these efforts, can be summarized by the phrase DevOps for ML. If you don't take anything else away from this talk, this is the phrase to take away. I've also heard it referred to as ML Ops, so you can take away that if you want it even more concisely. And then the final thing is how to achieve this. Full disclosure, what I mean by that is Dot Science is a product that is being sold. We have a booth downstairs in the booth room, and I will be talking about how ML can be operationalized, and then the message will be, if you don't want to do all that yourself, then Dot Science can help you. So we'll start with AI efforts today. And this is a theme that I think is being repeated many times, especially at this conference, which is AI has a huge potential, but it's still an immature discipline. It's the Wild West out there. People are attempting to operationalize AI, but there are now damaging levels of chaos and pain. People are losing money that they should have made because they are not doing AI properly. Some of the key problems affecting AI today: wasting time. Things are just inefficient. People duplicate work. There's just a lot of stuff that should be done more quickly if it was made easier. Inefficient collaboration. People have ad hoc teams. They may have steps in their process where you have to talk to somebody. I think there was an example this morning, like the Slack thing. Did you do this model? Did you put the parameters up for whatever? And there's just, if you have any kind of asynchronous time zones or anything in your company, it's not going to work. It's not as efficient as it should be. Kind of related to that, manual tracking. So a lot of, especially data scientists, come from various backgrounds where versioning your work is not a natural part of what you are doing. They might be scientists like me, or they might be mathematicians, statisticians. What they're motivated by is exploring the data and solving the problem and documenting everything they did by versioning. Not everybody does it. Reproducibility and provenance. Similarly, you do something, you may not even know yourself what you did a week later if you come back to try and see what you did. And similar to reproducibility, provenance as well. We analyze this data. Where did the data come from? Not sure exactly. And finally, models are in production, but are they being monitored? And so on, and so on. These are just a few examples to illustrate this. A few quotes from real people. So in retrospect, if we had been able to save the versions or gone back in time to see how he got his learning rates, he being some data scientist presumably, it would have avoided a lot of questions from the auditors. Auditing of machine learning is not particularly common yet, but it's only going to become more so, especially in the regulated industries and especially as regulations increase. Another quote, 2 of the data scientists who worked on that model have left. The phrase have left is very common, especially around here. You want to be able to see what they did, but you can't understand it or they didn't know, and it's gone when they're gone. One model failed for 3 months and we lost an immeasurable amount of money. That is definitely possible, especially with complex nonlinear machine learning models. They can go from being highly accurate to spewing garbage in literally a second because something changed and you don't know unless you monitor it. Couple more. After the last audit, I was surprised how many problems there were, and they could have been solved by keeping paper logs. I personally think this is slightly melodramatic, but if we ask our data scientists to do this, they will leave. Well, possibly, but they certainly won't be happy, and it's not particularly reliable anyway. And then lastly, we keep our data scientist teams small. Well, don't even need to read the rest of the quote. That's probably a problem to start with if you're trying to do anything on a large scale. We keep them in the same room so they can track their summary statistics by talking to each other and remembering. Well, enough said. So what is needed to get past these quotes? Well, it's the phrase from the start, DevOps for ML. So this will talk about what is needed, and then the third section will be our suggestion on how to do it. So we have in fact been here before. In the 90s, software engineering was siloed in many similar ways to this. Things were not version controlled, there was no continuous delivery, and software took months to ship. These days, AI takes months to ship, many times if you're doing it in production. Software went from months to minutes, and we believe the same is possible for AI. So these are the requirements to achieve DevOps for ML. And if you go on the .science website, this is in fact what we call our manifesto. There's even a little tab that says manifesto. And so you can read this and see more details. But in a nutshell, there's 4 different things required to achieve DevOps for ML. The first is reproducibility. You need to be able to go back to a model that was for months ago and rerun stuff and get the same results. Your models must be accountable for both ethical and legal reasons. You must be able to trace back from a model that is in production and outputting stuff that can have consequences for real people's lives, and be able to see what exact model was run, what data was it run on, why did it take its decisions, the provenance. It needs to be able to stand up to to full auditing. The third thing is collaboration. Any team of data scientists beyond the small team of people in the same room, and sometimes not even that, needs to be able to collaborate in a coherent way. Asynchronously, if somebody leaves, somebody else needs to be able to see what was done and understand what was done, and so on. And then finally, you need continuous deployment. If you have a lot of models, a lot of data, you don't want to be having error-prone manual steps in your deployment process. And likewise, you need to be able to monitor things statistically. So why not just use software development tools? Well, as we've again seen in other talks, data engineering and machine learning is not the same as software development. Software development here we're showing as being code, test, deploy, monitor. Makes it look easy, but it's not. But machine learning in many ways is even more complex. As you can see, the process has more boxes. And and so the fundamental thing with machine learning is you have to track more stuff. So you've not just got the code that's being run, you've got the data sets, and then you've got the models, and the models can have parameters, hyperparameters, literally hundreds in some cases. And you've got the metrics that the models are putting out. The metrics are crucial because they often tie directly to your business value. All of this stuff has to be tracked. Otherwise, you're not really recording what was done for machine learning. And then there's the whole training models plus deployment and monitoring. And it's not just models, it's also data preparation and feature engineering, as anyone who's tried it will be well aware. You track all this stuff, and in .science, the idea that we have is you track what we call runs. So there's a part of the code where you say, this is the start of a run, then you do whatever, prepare your data, run machine learning. Everything is versioned, and then you say this is the end of a run, and then that is tracked within the system. And we'll see that in a few more slides. But what this does is it provides the context for the reproducibility and the provenance, and it gives the accountability. This just shows that in another way. So if you look at the box where it says development, the box at the bottom where it says data engineering, typically starts there. And a lot of companies that want to do AI, they have a data lake with a bunch of raw data in, and that's where they're starting. So you have to do data engineering, and that's where our idea of data runs comes in. Then you've got the model training, then the development, and then the deployment, then the production. And you can see how things cycle round and round. So you've got something in production, then you've got some more data coming in for training, and you can see data runs, model runs. Basically, all of this stuff needs to be tracked. So how to achieve this? This is the part where I will tell you a way to achieve all this, and then the message will be .science can help you to do that if you are so inclined. So the fundamental thing is version control. Everything has to be version controlled, and doing this automatically is the only way you're going to get all the data scientists to actually do it. So the version control underpins everything else. First thing it underpins is the development. So you want to do reproducible machine learning. What stuff do you have to version control? Well, for a start, the environment. As we heard before lunch in this room, different environments can give you different results, even with the same model and the same data. For example, as they said, CPU versus GPU. You have to track the environment and all the libraries and everything else. Otherwise, you are not guaranteed to be reproducible. You have to track the code that was executed. And often that would include, for example, tracking notebooks. Data scientists like to work with the Jupyter notebook, which is rather more than just a text file containing code. And the stuff that went in, the parameters and all the rest of it. And you have to track the data, the versions of the data. And the data may be very large, far too large to keep in Git, for example. So how do we do this? 3 different things. So pinning down the environment, well, that's a relatively well-settled solution at this point, I think. Docker has been a big hit in the DevOps world, and it can be a big hit in the ML world as well. Lets you pin down the execution environment. And then versioning, well, Git is the de facto versioning system. Developers have been using it for a while now, as we know. But Git is not perfect for data science for several reasons. It lets you track versions of your code and collaborate in the usual ways. But data science, you don't commit every time something changes, because that would be kind of crazy when you're iterating through a model or doing a grid search or AutoML or all that stuff. But at any point in this process, you may generate important results because one of the models in your grid search is probably going to be the best one. You may then retrain on the whole training set, whatever, but it's still an important result. Git doesn't cope with very large files. I've seen machine learning demonstrated with a training set of a size 1 terabyte, and you can't put a terabyte size file in Git. And data scientists often, especially in the early stages where they might be trialing stuff on small data first, will mingle the code and the data anyway. And then Jupyter notebooks are not easy to diff and merge. So this is really one of the more substantive proposals that .science is making. .science is built on top of a product called .mesh, which is open source, and .mesh is based on the ZFS file system. Essentially, it's a Git for data. It handles large data very efficiently, terascale data sets, and so, for example, you might run again on a large data set. You only have to track the difference each time. You don't have to load the data, copy across all the data every time. ZFS and .mesh are well established at this point, so that's the strong foundation that .science is built upon. And then further, we have the other stuff that it can do, like tracking metrics, tracking lineage and provenance. You can diff and merge your notebooks, and you can do pull requests. So that's development. Then there's the 3 other boxes. If you can't read this at the back because it's too small, don't matter. What it says is it's nice to develop stuff in Jupyter, but then you need to deploy it. So you need to have a continuous integration system and continuous deployment system, which runs against the version data, creates a version model, lets you track your metrics, and puts the model into a repository where it can be deployed. From the repository, the model can be promoted into production, and there should be no manual steps. And this is the thing where you can set it up yourself, but .science can help you do this. Deployment into production, Kubernetes is a common thing. Not every data scientist can set up Kubernetes by themselves and have a production system that is business critical. So this is another area where we propose to help. And then finally, just as important, model monitoring. And this was mentioned again in other talks. A common combination these days which you can use would be, for example, pushing the outputs of the model to the time series database Prometheus, and then pairing that with Grafana to see visually what's going on. And a key point with enabling a setup like this is you can query the Prometheus with a query language, and that allows complex queries and functions. So you can monitor, for example, the distribution of your predictions and then set an alarm if something changes, and sort of any other complex function that you need, because you need a lot more than just thresholding to monitor machine learning models in production. So that's what .science is proposing to help with. And to summarize, business AI efforts are mostly ad hoc. There's the cliche, 80% of AI projects fail, and there's a reason for that. Ad hoc is at least part of it. Thus, we need DevOps for ML. You need to track and version everything. You need to have a notion like runs to track stuff. You need essentially a Git for large data. That's the .mesh plus CFS file system. And you need things to be easy to deploy from the training and experimentation through to production. This can be achieved if you have a team of data scientists and data engineers and machine learning engineers and a lot of time and a lot of resources, by combining a bunch of different tools. Or, you can guess what I'm going to say. If you're not willing or not able to do all that, then .science is a possibility for you. So I'll just say, if anyone wants to know more, please either email me, nick@.science, fairly easy to remember, I think, or you can come and visit our booth downstairs in the big room to the right of the registration desk, or you can go online and look at our demo. Thanks very much.